All right, these are the nature of science measurement slides. All right, so this was the original question. Was the metric or English system of measurement more valid? So in order to answer this, we did the metric versus English lab. Now, the first thing that you should have looked at is both the metric side and the English side. Now, if we're looking at the English side, that bottom one down there, uh, does what is the resolution of the ruler on this side? So if you look at that, each one of those little dash marks, the smallest interval that can be measured is 1/8 of an inch. Now, it asks this question, does it have an uncertainty digit? Why or why not? It does have an uncertainty digit because it's an analog instrument. If you're measuring something and it fell in between two of those lines, you'd be able to make an estimated guess to that next digit. So down to the 1/16 of an inch, probably. Now let's look at the metric system, that top one, the centimeter side of the ruler. What's the resolution of the ruler on this side? Does it have an uncertainty digit? Well, the resolution, let's take a look at each one of those individual dash marks. Each one of those little marks is going to be one 1/10 of a centimeter, or 1/1000th of a meter. Now, the next question is, does it have an uncertainty digit? And the answer is yes. It does have an uncertainty digit because, once again, it is an analog instrument. You can make an estimate to the next digit. You can make an estimate down to the 1/10,000th of a meter. Now, if the metric system were being used to measure the circumference of a can, and the line on the can landed exactly on the 20 centimeter mark on the meter stick, how would this measurement be recorded in the data? So I gave you a couple of options: 20 centimeters, 20.0 centimeters, or 20.00 centimeters. It would be recorded as 20.00 centimeters. And it's because, well, the resolution is down to the 1/10th of that centimeter, right? So 20.0, but you also have to include that uncertainty digit. If it's exactly on the line, well, you can estimate the next digit is going to be a 0. So this gives you 4 significant figures. All right, so the metric side, you can see the resolution, and the English side, calculating things on the English side with the inches gets a little tricky because it is in fractions. So if it falls on the like 2, and then on the third dash, it'd be 2 3/8, or 2.375 inches. So in this lab, you were to measure the diameter and circumference of all 3 size cans in the English system, so the inches side, and place the results in the Google Sheets that was attached. And then you would do the same with the metric side. So you can see here down at the bottom, measuring the diameter is fairly easy, just straight across the can. That's what the diameter is. Now, circumference is a little bit tricky because on each one of these lines, there's a little dash mark, and you roll the can on the meter stick, and where that line ends up, that will be the circumference. So when we did this, this is the data that I got. So you can see here that you're looking at this is the can, and then it gives you a nice graph with the slopes. Now, the R squared value, that just tells you how you can predict future data points based on this data. 1 is a perfect score. Anything less than that is there might be a little error, but you can see on both of these, okay, there's some, like, I did these measurements correctly because the R squared is 1. All of them fall on the same line. So let's answer these questions. So let's look at the equations for the line on each graph. Come up with a good scientific claim to describe the slopes of the lines when comparing the English and the metric graph. Remember, for a claim to be scientific, there must be a test for something. So if I'm looking at this, right? So if I'm looking at this, I know that this one up here, the slope, is 3.15, and down here it's 3.13. Well, why do you think that would be? All right, so I can look at this and I know the slopes are going to be the same. It doesn't matter whether it's the English system or the metric system. The slopes of this line is going to be the same when I'm graphing centimeters over diameter, right? Now remember, slope is rise over run. So centimeter divided by diameter, right? So if you look at this, it's just going to be pi, right? The circumference divided by diameter, that ratio, no matter what unit you're using, is going to be pi. So you can see that, yeah, that slope is going to be close to pi. So let's, based on that, right, based on the fact that the slope of this line, I'm taking the circumference by the diameter, the ratio of the circumference divided by the diameter, and I'm going to get pi. Based on the data from this lab, does the English or metric system of measurement provide a greater level of accuracy? So the answer to that is going to be They're both. They both provide the same level of accuracy, and that's because, like, if you're using the inches and you say, "Yep, this is 20 inches," well, that's the accepted value. If you look at it and you say, "Oh, it's 49 centimeters," that's the accepted value. They're both just as accurate. Now, what about precision? Being able to get the same result over and over again. Well, if I'm using the same ruler and I'm using inches, I'm going to get the same result over and over again, right? It's just as precise as a metric system if I use the metric side and I get the same centimeters over and over again. Now, this last one is tricky. Based on the data from this lab, is the English or metric system a more valid system of measurement? Explain your answer. So to answer this, let's take a look at this, right? So if we came up with our own unit right now, it doesn't matter what it is. I take a piece of tape and I say, this is the new measurement unit. Well, your measurement is going to be just as accurate, just precise, and just as valid as the metric and the English system, right? Just as valid, just being able to use it. And it's because that's not changing what you're measuring. If I made up a unit of length, the ratio of the circumference to diameter is still going to be 3.14159.265. Now, where did all these measuring systems come from? All of these systems of measurement were just made up by humans, right? They're all made up by humans. Think back to that black box experiment. There was no box that we just opened and said, yep, here is the measurement system that we have to use for our for like science, right? We had to come up with our own, and it doesn't matter whether it was the English system, which was invented thousand years ago, the metric system, which was hundreds of years ago, or one that you just made up uh, in a couple of minutes. They're all just as valid. They're all going to be just as accurate. All just going to be precise. They were all made up by humans. So let's take a look at some at like the second, right? So what is the definition of a second? So you all have an idea of what a second is, right? And now on a side note, like just a billion seconds is about 31.7 years. You can look up your birthday. There's a photo of me on my billionth second. Um, and it was just a fun little thing to do because I have a billion seconds. So in your just think about what is a second? Like, how do we measure a second? And can't just say one tick on the clock, because then I'd ask you, well, how would you determine how long an interval does that tick represent? So go ahead, just think about that. Like, how do we measure the second? So if we look at this, right? We all tried to measure things based that were same for all humans on the planet Earth. So people used events that happen for everybody, right? So if the day, it takes the same amount of time for the sun to return to the same spot in the sky for everyone on Earth. Now the year, it takes the same amount of time for the Earth to revolve around the sun for everyone on Earth. So that means the summer and the winter solstice happen at the same time for everybody on the Earth. Same thing for the equinox. The vernal and the autumnal equinox happen at the same time for everybody on the planet Earth. Now, 1 year is divisible by a day by 365.2425 days. So in order to prevent like some drift, they had to add a leap year. Now, here are the rules for the leap year. It gets kind of tricky. Well, the year number must be divisible by 4. Except for end of century years. So that means that like if it's the year 1900, that's not a leap year. But if that end of century must be divisible by 400, so that's why the year 2000 would also be a leap year. So you can see there's a nice little a flow chart over there that can determine whether it's a leap year or not. All right, so the second, right? Let's take a look at the second. In 1967, the second was defined as the duration of 9,192,631,770 oscillations of the valence electron in the cesium-133 atom. So you can see here that cesium atom does have a valence electron, and it switches energy states at a fairly relatively predictable pattern, and every time it oscillates this many times, we just say, yep, that's a second. Now that would give us a very large resolution, or a small resolution of a second. Now, what are the benefits of measuring the second this way? Well, all cesium atoms all over the universe will oscillate the same way. It's based on something universal. So same thing with the meter. right? So if you hold up a meter stick, that's just going to be a good representation. Now, it has changed throughout the years. It's been based on the pendulum swing, fraction of the Earth's, like it used to be 1/10 millionth from the equator to the North Pole. Then they switched to like a physical rod in a place, and they did it at different temperatures, different materials, so they could get, hey, this is exactly a meter. But now the meter is currently defined as the length the path traveled by light in a vacuum in 299th millionth 792,458th of a second, with the second being defined by the cesium atom. So the benefits of measuring a meter this way, well, the speed of light in a vacuum is the same all over the universe, and the cesium is like that's going to be the same. So this is based on something universal. It's going to be the same everywhere. There is an exact defined definition for the meter that does not change. So the metric system, right? So why do we use the metric system in science? Well, the metric system is used in science for two reasons. Number one, it is universal. Everything that is measured is defined as constants of the universe. And also it's base 10. It's easier to use. So like I said, that black box experiment, we had to make our own system of measurement. So it was just easier for us to use the fundamental like rules of the universe to make our own. So we have an exact definition for everything that we're going to measure. But now let's just say we're converting within the metric system. Does that affect the resolution and the significant figures of that measurement? So remember, these are the rules for those significant figures. 1 through 9 are always significant, leading zeros are never significant, and captive zeros are always significant figures. But trailing zero is only significant if it has a decimal point. So like I said, like here's an example. Hey, I'm looking at somebody that says, yep, they weigh about 180 pounds. Well, the 1 and the 8 are significant. The 0 is not. That's just a placeholder. That's two significant figures. Now, if I stepped on a scale and said 180.0 pounds, well, yeah, those zeros are measured. So that has 4 significant figures. So when we convert within the metric system, it's real easy. All you have to do is just move the decimal point. So you start at whatever prefix, move the decimal point that many spots. So if we're looking at like a metal rod, right? A metal rod has a measured length of 30.00 centimeters. Well, how many significant figures does that rod have? Well, it's 4 significant figures. Trailing zeros are only significant if there is a decimal point. There is a decimal point. So all of these are significant. Now, convert this measurement to meters. So I have centimeters right here, and I move it to the left, 1, 2, to the basic unit, and I'm going to get 0.3000 meters. Now, notice this has 4 significant figures. I did not drop those zeros. Those are significant. Those were measured, so you have to hold on to those. Let's take a look at another one, right? So now a metal rod has a measured length of 0.25 meters. So this has 2 significant figures based on this rule. Convert the measurement to millimeters. So I start at meters and I go to millimeters. Now I'm going the other way. 1, 2, 3. So I go 1, 2, 3, and I add a 0. Well, this has 2 significant figures because I did not have the resolution or the uncertainty digit to measure beyond that 5, but I needed that placeholder. So this is going to have 2 significant figures as well. So you can probably already guess converting within the metric system does not affect the number of significant figures. In order to reinforce this, we did the ruler of the world lab, where we used a transparent meter stick, measuring stick to measure the length of certain lines. And then the resolution, well, is going to be 1/10 of a centimeter. Does the transparent measuring stick? Yes, it has an uncertainty digit because it is an analog instrument. Now, what we did was we measured this, right? Now, what I want you to see is that we measured and then converted to different lengths. We measured in centimeters and converted into different lengths. But what I want you to see here is that, yeah, that first one landed exactly on the 23 centimeter mark. So the resolution was 1/10 of a centimeter, but also I have to include that uncertainty digit. If it's exactly on the line, I can say, well, that next digit's going to be a 0. Now, this has 4 significant figures. Now, when I convert, this has 4, this has 4, this has 4. I don't drop those zeros. That is what that is. It does not affect the significant figures. Now, this one was a little tricky because you were to place that transparent measuring stick on top of the wooden meter stick that was back there. Be sure to line up all the 0 lines on the ruler. Do the lines match up perfectly? If they don't, so you can see here, well, yeah, they start to match up down here, but as you get to 20 and then 30, it's off by a whole millimeter. Now, if they don't match, what could be done to figure out which measuring stick is more accurate? So I've got two different things that say this is the centimeter, but you can see here they're going to be off by a little bit. So I've got two different competing units for measurement that call them the same. Well, what can be done to figure out which one's more accurate? Then answer this question: what is used to define the meter? So remember, we just learned about what the meter is. Remember, the metric system is used in science because all the units are based on something, right? It's going to be based on something universal. Remember, the meter is defined by the length that light travels in a vacuum in a certain amount of time. So it's based on something universal. So yeah, one of these is going to be more accurate than the other, and we have an exact definition to compare them to. So this last one, we kind of already answered these. What using it did not affect the significant figures when you converted, and that's because the only thing that affects the significant figures when recording is going to be the resolution and the uncertainty digit. All right, and that last one is identify any systematic errors. So here's some systematic errors right here, right? That meter stick or that ruler that we were using might not have exactly been a meter, right? It was just a representation. So you can see that the centimeters might have been off. That's one systematic error right there. And you have to ask yourself, well, does it affect the accuracy or precision? It's going to affect the accuracy, because even if I use that meter stick that might be off by a millimeter, I'm still going to get the same result. It'll be precise, but not accurate, right? And what could be done to mitigate that systematic error? Well, we could compare it to other rulers, see if it matches up. All right, and then there was a secret code once you answered all the questions right. So once again, there is just too much unknown in the universe to take a break from learning and get out there and question everything.